Hi. Here, wait, okay, there's music playing. Okay, so what's up? Folks, welcome to another video. This is going to be an explanation of, a new system I'm doing. I think I already recorded something like this, but I deleted the recording because it sucked. So, I'm doing this. If you don't know, there's this YouTuber named Artifexian. And I wouldn't say I'm a long-time subscriber, but I've been with them for like half a year. Major fan supporter of the channel. They recently did a revamp of their whole setup. Took a lot of courage to do that. They're doing a whole new thing. They're doing what they do, but they're doing a new project, and it's going to take a long time. And I'm going to do a project like theirs alongside them. Although we're taking slightly different paths, but we're playing by the same rules. It's a world building project. It has 3 stages. The first is this stage, is actually world building, building the world in terms of the galaxy, the solar system, its history, and the planet. Next, we're going to do some speculative biology, going through a few billion years of history as the planet, evolves its life, and then eventually reaches intelligence. And third, we're going to do conlanging, and I don't know if they're going to do nation politics stuff. I'm going to do some nation politics stuff, at least a little bit. I'm going to turn this down because I don't know if it's like drowning me out. That is probably fine. Anyway, so after they're done with that, the conlanging, they're probably going to stop, but I'm not going to stop there. I'm going to take it further and go through the space age, because I am a big league space fan. I'm a big league space fan. So I want to design the system in detail, and I want to have them be able to name each of the planets in a language and have those names be carried on despite the languages themselves evolving or becoming extinct or archaic. And then they're going to go through exploration of the bodies. They're going to launch probes, uncover the history, uncover the secrets of their geology, their astrophysical anatomy. That's the same thing as geology. They're going to discover the stuff about them. And then they're going to, the nations are going to get involved, and they're going to start colonizing objects. And then they're going to start going out from here to the other stars. So that is my project in contrast to theirs, but I'm going to do it alongside them. Now, the first thing that I've done is I've made the solar system. And let me change the song because this is just a bit extreme. Let's see, maybe, no, let's see, yeah, this song is like 15 minutes long. Alright. So, here, wait, let me turn it down just a little bit more. There, I think that's good. Okay, so let me explain the solar system in order. And I had it going at extreme speed just to make sure that it was stable. Because I'm going for realism here. So this is 0.1 million years or 100,000 years into the simulation. I've just left this on. And as the simulation's been going through, I've been tinkering with orbits, adding new objects, deleting objects for simulation speed's sake, but keeping those objects in my mind present. Basically, this is what we have so far. So we have, count them, 1, 2, 3, 4, 5, 6 major planets. And we have 2 asteroid belt dwarf planets, 1 planetetesimal, or planemo, and 1 asteroid remnant in the inner system. And we got the asteroid belt where these two dwarf planets are, and we have the Kuiper belt beyond the ice giant. And they got moons. I have moons in my plan in my head for them. Yeah, none of the inner system objects though have any moons, but I'll get to that. So let's go in order. And none of these objects have their official names yet. They're just their technical names, because I want to name them in the language that I'm going to create when Artifexian gets around to creating the language. Because I'm relatively new to conlanging, so I'll just write off their tips and pointers, I guess. Yeah, it'll be great. So, let's start with the first object, the star. This is a K-type star. It's a K0, meaning it's one of the largest of the K-type stars, at least I think. That's what Artifexian's spreadsheet spat out for me, is that K0 is what this star with this mass is. 0.3876 is the exact mass, but Universe Sandbox clocks that in at 0.838. But it doesn't really matter, so alright. That's a K-type star. It's 7.5 billion years through its life cycle when complex life starts to develop on the temperate terrestrial planet, the main world with life. This is the main world with life, the one that we're going to focus on. Yeah, so that's the planet. Here, let me go to the spreadsheet and check what the nearby stars are. So I am using the spreadsheet for the statistics and all that. It's the Galaxy tab. Okay, so the stellar neighborhood is in a radius of 10 light years, so it has a reach in any direction of 10 light years from the main star. The main star is a monosystem, a classical system of one K-type star. Out of 2 K-type stars, there's 1 G-type, 1 F-type, 13 M-types, 2 white dwarfs, and 3 brown dwarfs, with a total of 22 stellar mass objects. Now, what are these numbers, letters meaning? Well, let's start from the highest, go to the lowest. F-type stars are a bit more massive than our sun. They are usually like a pale white. They can be blue, but just blue. Only just. G-type stars are the mass of the sun. Pretty self-explanatory. They range from yellowish to whitish. K-type stars are this star in my sim here. They range from yellowish to orangish. And M-type stars are red dwarfs. G-types are yellow dwarfs, K-types are orange dwarfs, and M-types are red dwarfs, named because they range from red to orange in color. And then white dwarfs are dead corpses of stars that can reach the red giant stage. They're the remnants of, I want to say, from M to either F or A type stars. Maybe B. I doubt O, though, because B and O type stars die in supernovas. A is kind of weird. I think the main jump goes between A and B for supernovas. But O-type stars are the largest stars, the largest main sequence stars in the universe. Main sequence are stars that can have, normal classical planet systems, like our own. B-type stars are less massive, but they're still blue and enormous, and slightly more common, or a bit more common, a lot more common, but they're both really uncommon stars. A-type stars are bluish to white, F, G, K, M, we already did those. The D-type would be the white dwarfs. They're the dead cores, not just corpses. They're cores of some of the main sequence stars. Our star, the sun, will become a red giant, bloat, and die, and its core will be left over as a white dwarf. So they're dead stars. They're dead cores of stars. Very old. Brown dwarfs are stars that were forming and could have became main sequence stars, but they weren't massive enough to ignite in stellar fusion, so they're kind of just big balls of gas that aren't burning, which makes them both. It's weird. Brown dwarfs are a cross between a star and a planet because they could be considered really massive gas giants that didn't form around a star, but they could also be considered stars that just didn't form. But they're both, so they're considered both. So they're kind of their own thing. Brown dwarfs, not really their own, but we just call them a separate thing. Anyway, this calculator that Artifexian put up also calculates the types of systems: single star systems, binary stars, and triple star systems, and then quadruple stars or more. Single star systems are like our solar system and this one, the one right here. They're systems that have only one star, and there's 9 of them in my stellar neighborhood. Binary star systems are systems with 2 of these stellar mass objects orbiting each other in their own system. You could have close-knit binaries where there's like 2 stars really close together, and then the planets orbit those 2 in general, or a star system can have 0 planets. It's possible. Yes. So there's 5 of those in my stellar neighborhood. Triple star systems, there's only 1 of. That's where stars can orbit 3 in one system. You can't have for binary and triple and above 2 or 3 stars that orbit really close together. I think for more than 2, that gets really complicated. But you can also have them orbit really far away so that they orbit each other as they move through the galaxy and they don't separate ever. But they also have their own planets, not planets that they share together around their barycenter or their center of mass, the point which they appear to orbit each other. I have already made a system in the stellar neighborhood that's like that. It's not the closest star, but it's like the second or third closest star, and it's a binary of a G-type star and a red dwarf. So it's like a sun, but with a low mass star orbiting it. They're really close together, and they have about 5 planets shared between them. It's really similar to this system. In fact, it was the original system. I just added a 3rd star in the distance, so it's actually a trinary. I could remove that star and have that other system be... You know what? Whatever. Ignore everything I said for the past 3 minutes. So yeah, there's only one trinary system, 2 binaries, and no, not 2 binaries, 5 binaries, and 9 single star systems, which makes in total 15 solar systems. Why can't I talk? Solar systems within the stellar neighborhood. That's a tongue twister. It also spits out a coordinate generator, but I think that I could leave that up to moi for the coordinates. Anyway, the sheet has a planetary system calculator. I used that to my liking to get a sequence of stable orbits, which are spaces, imaginary orbits that planets can have to where they won't really interfere with each other that much. So, here I have the 6 major planets were the first thing that I introduced in the system. Then I added the dwarf planets and the remnant and the planemo. So yeah, that's that. Let's get into stuff beyond the star. Also, the star doesn't flare as much because it's, a K-type, and it has to not flare that much in order to be a habitable system. So, let's go with the first planet, the cool Venus. So I've been letting the simulation run, and what I planned to do was to have this be a planet that had water, but it couldn't liquefy. It was just gaseous. The reason why I called it a cool Venus before I placed it down was because I wanted it to not have a thick atmosphere that blocked light from hitting the surface and caused a renegade greenhouse effect. I just wanted it to have a really thick atmosphere, like up to twice as thick as Earth's, and be very warm. So warm that at the very least equatorial water on the equator and lakes and oceans on the equator couldn't form without evaporating, which is why there's none on this planet. But What was interesting is when I placed it down and let the simulation run for tenth millions of years, 100,000 years, the poles of the planet kept getting water and ice caps as the orbit changed. So the planet is going through periods of cooler and hotter phases as its orbit changes dynamically because it's interacting with all the other objects in the system. Most notably, this second planet out and the dominant Jovian planet. But mainly just this one, because it has a slightly eccentric orbit, and when it gets closer to this planet and they're at their closest points to each other, coincidentally, that can change the orbit a little bit. So it's constantly evolving. Even though I've placed this stuff... My tongue is carrying so much weight. Even though the system has already been set up, it constantly evolves, which is why I've had it running for 100,000 years, so that it can stabilize, quote-unquote. Anyway, so the cool Venus has one permanent water region, and I think this is a permanent lake. At the South Pole, there's permanent water deposits. They do freeze, and they do shallow as water evaporates from them, but for the most part, it's the most frequently liquid area, and it counts for like 70 or 80% of the planet's history being wet. There are spots here that are permanently liquid water, so that's kind of good for it will not have life on it, but it is habitable. All three of the interterrestrial planets have water on them. They're just varying degrees of temperature. For the North Pole, it only gets, or the Northern Hemisphere, the northernmost Hadley, whatever, the top third of the planet, only gets water during cool parts of its year. During hotter parts, it's completely dry. So there's not a whole lot of chance for permanent settlements up here, but there are chances for permanent settlements at the South Pole. So that is the cool Venus explained. Now for this. This is literally just an asteroid. It's potato-shaped, which I love. It looks like a little potato. So I'm running with that. A canonically potato-shaped stellar, not a stellar, remnant from the formation of the solar system. When star systems form, classical star systems that is, they start with the formation of the star, which is in a nebula. Okay, so picture the scene. New timeline. There's a nebula. It is the guts spewing out from an exploded dead star. Stars, or the most massive of them, explode when they die, and they launch a bunch of gas into the galactic space, into the space of the galaxy. Now, some of this gas can get really close together, sheerly by chance or by other events going on. Usually by other events going on. Like supernovas elsewhere in the galaxy send shockwaves into the nebula that disturb the dust clouds and bring them closer together. Or it could be a passing star that creates a sort of wake of gas in its wake, and that gas gets closer together, and that can form a star. But one way or another, gas becomes closer together, and it starts to form an accretion disk. Oh, my ambient sound in the background just reset. Okay, wait, we're gonna wait for it. So yeah, the gas is attracted to itself by its own gravity. One gas particle is attracted to another, and another, and another, and all the others. And while the gravity of one gas particle is not a lot at all, the galaxy of the entire cloud is a lot, and that keeps it together. Barely, but it keeps it more together than it falls apart. In fact, more than would be stable. So, it constantly gets tighter together. It constantly proceeds to collapse into its center point, its core. The core of the protoplanetary disk will become either or one of these stars. So the earliest on material in the disk is hydrogen and helium and other trace elements. There are other elements like carbon and silicon and iron and plutonium, although the lighter the element, the more common it is, so elements like plutonium are really rare. Elements like iron and heavier are in their own category of rareness, along with all the heaviest elements, because they can only form when the most massive stars undergo the most extreme deaths. And certain elements, that's not a word, certain elements, like, say, plutonium or gold, can only form when dead stars collide. Neutron stars, when they smash together, they create the fusion necessary to create even heavier elements like gold. So, our gold bars came from the guts of dead stars as they smashed together and spewed their new guts that they created when they merged out into the universe, into the nebulas, just because they, like seeds in the wind, they just go into the galaxy and mix with the whole thing. And there's constant amounts of these things going off all the time. So, yeah, so that's the material that's in the disk. But mainly, large majority, absurdly overwhelming majority, is hydrogen and helium. There are some molecules, simple and complex, that are universally common, not abundant. There are some abundant ones, like water, but there are common ones, like some organics, which can form from natural processes, although they're not exceedingly common. Our system is going to have organics in it as it forms, so that the planets can get organics on them, and 2 of them can have life, and 1 of them can have intelligent life. But 3 of them can be habitable, and all that jazz. So, what was it? Oh yeah, the system forms. So, as the core gets more gas and dust handed to it from the protoplanetary disk, it collapses to a point where it can, well, actually, at this point, it can take 2 paths. A, it can become a star, or B, it can become a brown dwarf. Brown dwarfs form when this cloud of material isn't large enough, and it spins a ball, but it doesn't crush it together with a final oomph and spark a star. Well, stars don't really spark at a set point. It takes a long time for them to quote-unquote ignite. But I learned that recently, so that could be wrong information. They could spark at a defined moment, but they don't turn into stars. Our system obviously does have a star, so this cloud of material did crunch together and form a star. In this system, that star formed gradually over, a few million years, right? So, that's done. But that isn't everything that happens. Obviously, there's planets where they come from. Well, there's a few things that happen when the star is formed. During the point when the star is igniting, the first planet forms. Now, as the star begins to warm up, as it becomes a star, it pushes back a radius of heat. This is both the star's habitable zone, but also the region at which it melts and vaporizes all ice. It's called the frost line. So the frost line is pushed back to a certain point, and that point gradually increases as the star grows older, but when it forms, it's at about the point where the first planet forms. The first planet is the largest gas giant, which I have called the Jovian Dom. Jovian for Jovian-type planets that are like Jupiter or Saturn, but mostly Jupiter, because Saturn is really not dense, which is kind of weird. But there was also a second planet. This one, I'll get to that later. But anyway, fast forwarding. After the first planet or first 2 planets or whatever have formed, and the star is pretty much in the game now, there exist 2 regions. The inner system, inward the frost line, inward the orbit of the dominant gas giant, and behind the frost line, where ice can and does exist. Inside this area, ice can't exist. There could be trace amounts of ice hidden in asteroids that form as dust particles stick together and go from dust to grains to pebbles to gravel to rocks to boulders to asteroids. And, they could be hidden inside asteroids. To mountains asteroids. To extreme asteroids. To planets. Anyway, the inner system doesn't have as much water as the outer system does. But it does have a bit of water in it. So, there's that to consider. So, let's see. I'm thinking. Here, wait, let me make sure this song isn't gonna finish yet. Let's just bring it back a little bit. Okay, so. Anyway, that's how this remnant exists. It is an asteroid that has survived all this time. The first objects in the inner system were asteroid-sized objects. They stuck to each other, and then those sticks stuck to other sticks, and then those just bound up and snowballed into planets. In our solar system, we don't really have a whole lot of remnants except for the asteroid belt and the dwarf planets and a few, comets that duck in and out. But we don't really know of any asteroids that are in the inner solar system that have really circular orbits. Like, inward the orbit of Mars and really circular. So, this is something that doesn't really exist in our system. It's a potato-sized, or potato-shaped asteroid remnant from the formation of the solar system. The reason why we don't have any is probably because it all got scooped up by planets. This could have formed a bit further out and got pulled in. It could have formed inward the star from the orbit of the cool Venus and got pulled out by the Venus. It could have formed where it is and stuck there. Either way, whichever way, the object is here, and it is in this orbit, very circular. In fact, a bit more stable than the cool Venus, which is interesting. Anyway, on to the third planet, the temperate Terra. Now, when it comes to water in the inner system, it's interesting because while there is water in the rocks, it's kind of trapped in the rocks. So there's water beneath the crust of Earth and beneath the crust of this planet. It has a wet interior. It's hot, but it's wet. So, where does the surface water come from? Well, it comes from the late heavy bombardment, which was when the ice giants Uranus and Neptune changed orbits. Neptune used to be closer to our star than Uranus was. Uranus used to be the outer planet. But because of a pass between Jupiter and Saturn, their combined gravity gave a little bit of a speed boost to Neptune and caused it to surpass Uranus and pull Uranus closer towards the star. So, Uranus became the 7th planet and Neptune became the 8th planet. They switched. But Neptune went a bit further out than Uranus, or it went out further than it is today and then migrated back inward a little bit. Whatever happened, it bumped into the Kuiper Belt, which was pushed back and shepherded by Uranus up until now. So there's a bunch of debris way out here. The planetary disk was massive. It was probably this big or something. But the planets only go out to this far. So there's been a lot of material out there for a really long time. And the ice giant, Neptune, came into contact with this little disk of debris that is called the Kuiper Belt. And it's beyond the frost line. So there's a lot of ice out here. And it's where the majority of Earth's water came from, at least on its surface. Neptune bumped into this cloud, caused a lot of its comet asteroids, a fuck ton of them, to wreak havoc all over the solar system. Their orbits went from being pretty circular or pretty eccentric but stable, not fucking with the inner system, to being slowed down so much that they dive in again and again and again for millions of years until they hit one of the planets or until they get ejected or something happens to bring their orbit to a stop of being really chaotic. A lot of these comets or Kuiper Belt objects hit the planets and give them water. So our system does have a late heavy bombardment. This object here, the Jovian Remnant, I don't know if I can do that. Well, yeah, I think I could do that. Okay, so the Jovian Remnant used to be the furthest planet, and the ice giant used to be inward, but they swapped. Or the ice giant used to be much closer, and the Jovian Remnant used to be a little bit closer, or its same orbit, and the ice giant got pushed back from about here to about here. So, the ice giant also butted heads with the Kuiper Belt, and also flew a bunch of Kuiper Belt objects into the inner system. And a lot of those Kuiper Belt objects smashed into the temperate terrestrial planet and gave it its surface water. This isn't supposed to be all green. It doesn't have any complex life yet. But it's whatever. Actually, I could change the color of this planet here. Hold on. Don't mind me, everybody. Just making a subtle change to a great object. There, that's actually kind of... It's alright, okay. So, this is the planet with the most surface water that it... liquid water. The most surface liquid. Liquid surface water. It got big oceans, okay? It won't actually look like this. It just looks like this in Universe Sandbox. You can only edit the surfaces of planets to a limited extent. I'm going to get into a bunch of tectonic stuff. This is a tectonically active world, kept warm by the heat from its formation and by the decay of radioactive elements. It has a dynamic tectonic system. Tectonic plate system. It got movement. It got continents and all that stuff. So, yeah, this is just a pretty visual of a planet similar to it. Yeah. As you may note, if this is the Earth equivalent, where's the moon? Well, you may think that I have moved the moon out of the simulation to keep it running faster, but unfortunately, on the spreadsheet, it does allow for a moon, and I added the moon distance, and it got it to a point that I liked. But when I tried to add it into the system, the star kept pulling the moon away. It was too far. So if you have, like, an object that's this far away from your planet, as time goes on, it's going to be pulled more by the star than the planet. And it's going to be pulled out of orbit and into its own orbit around the star. So it's not going to be your moon anymore. It's going to be another planet or Planemo object. So, Temperterra does not have a moon, unfortunately. It can't have a moon. The only moon it could have would be absurdly close within the Roche limit, or really close to it to where the two would be tidally locked. And I don't want to do that. So I'm just making it so that this object does not have a moon. In fact, none of the planets have their own moons. Very sad news. Anyway, wait, I'm not supposed to be here yet. I'm not supposed to showcase this bad boy. So yeah, also, since it has a molten outer core and a solid inner core, it's very similar to Earth. Iron-nickel compounds, molten metal moving very fast creates a magnetic field. So, this planet is protected from the star's radiation. This planet is... It has a different process. I don't actually know, because it's too small to have a liquid outer core. So it can't have a magnetic field like Earth does. But there are many other ways to have a magnetic field. For example, the gas giants have a completely different system than Earth. In fact, it's so different, we don't know what the magnetic field system is for the outer two most gas giants. Because their magnetic field doesn't originate from the center of their bodies. It's offset from the center. It's like halfway between the center and the surface. It's really weird. Also, it's not aligned at all with their axes of rotation. It's really weird. So, yeah, I can pull that excuse. There are things we don't know about electromagnetic fields. I can pull the we don't know, but it's there card. Totally. Anyway, this is a glacial planet. It is the Glacial Terrestrial. This planet is a snowball. It does have surface liquid water, but it is really cold and is not Earth-like at all. In fact, the equator is the only place where liquid water can form, and the continents are always covered in some sort of permafrost or snow. So it's a frozen planet that just happens to have a bit of liquid water. This simulation here bugged out and made the planet have really weird stuff. But just imagine it's like the Arctic at the equator and the extreme, extreme Arctic between Earth and Mars everywhere else. Good? Good. All right. It's a bit smaller, this planet, than the temperate, but it does also have a magnetic field because it's above 0.8 Earth masses. That's kind of the standard that a lot of people use, where if you're below 0.8, you can't really have an Earth-like magnetic field. So, it just happened to randomly be above 8. Well, it's not random. I decided these numbers, but I wasn't thinking about magnetic fields when I made these numbers. So, the number that I gave myself works, so I'm going to keep it. It has an Earth-like magnetic field. The equator has liquid water. It is a habitable planet. Another interesting thing, and the last object in the official inner system, is this, the Planemo. Now, it's another thing that our solar system does not have. There are, I think, 3 things in this system that our solar system does not have. Then again, none of these objects have moons of their own, or at least these inner terrestrial planets have moons of their own, so our solar system has something that this system doesn't have. Yes, the planetetesimal here, that's the word for a planet that was forming or in the process of forming or wanted to form or all that shit, but it didn't form. It didn't have enough material. It was starved of that material. It was robbed of that material. Or it was an ejecta from a collision between 2 planet-sized objects, and it survived to the present day. This particular object was going to be a moon of Glacial Terra. They formed really close together, and they were just going to become planet and moon. But, like I said, I can't do that, so the gravity of the star pulled it away. I originally wanted this to be an asteroid, but the more I thought about it, the more I was like, well, they're both going to clear this orbit with material. My original plan was to have the Glacial Terra be a super Earth, which is an object at least 1.3 or 1.5 times the size of Earth, but it's smaller than the largest inner system object, which is smaller than Earth. So, I decided, you know what, I'll just have both work. It could have been a super Earth, but its moon started forming, and it fucked its planet up, so it couldn't become a super Earth. And that moon was pulled away. So, it doesn't have the moon, and it doesn't have the mass, so it's kind of dwarfed. It's not really dwarfed. It is dwarfed from its potential. Because of the interesting circumstances of these two forming really close together, they share the same orbit. Now, you might be thinking, well, wait a minute. If you have these 2 objects share the same orbit, then doesn't that mean that eventually one of them will collide with the other? Because they can't be perfectly aligned with their orbits, and you're right. Also, even if they were perfectly aligned, the gravity of the dominant gas giant would pull one of them out, and their orbits would be offset. So, eventually, over the course of millions or billions of years, one of them would catch up to the other and collide, right? Not necessarily. The moon was pulled away really early on, and it was pushed back into the orbit at about this distance. Between here and here, generally. The civilization won't ever be able to narrow that down exactly, so why do I care? But it formed in that area. Opposites fifth the orbit of the Glacial Terra main planet. So why hasn't it collided? Well, it doesn't orbit the same speed as this. I think right now it's orbiting a little bit faster. Let me check its speed. Wait, I could check that speed anyway. So 25.7, 25.9. Okay, so it's moving slower than the Glacial Terra. So eventually it will be dragged behind its orbit while it catches up, and they'll meet. And you may think that it'll back into the Terra and collide with it. But you're wrong. As it gets closer, the Terra will have it slow down gradually. And when you have an object slow down in its orbit, the opposite side of its orbit starts to dip in. If you know anything about orbital mechanics, you know what I'm talking about. If the object is slower, the opposite side of its orbit becomes closer to its parent object, which means that when it gets to that point, it will orbit faster. So, since these objects orbit so close together, while it would eventually collide, it will take several orbits of this in order for them to back together. So, it will have reached the other side of its orbit by then, where it'll be closer to the main star and going faster. And if it's in front of it, and if it's going faster, it will start to go away. So, even though it sounds it sounds contradictory, as the moon planetesimal object gets closer to the main planet, it will be pulled closer, then slow down for half a year, and then speed up half a year later and start to move away from the planet. And if it reaches the same speed, it will never, because that's impossible. There's too many outside forces acting on it. I'm mainly talking about the gas giant, but I'm also talking about the Temperatura. So, also, nothing's ever perfect. They can cross a perfection, but they can't align with a perfection for long. So, whenever the planet is ahead of it, it will be pulled, slowed down, fall closer to the star half a year later, speed up because it's closer, and then move away, forward. And then it will move on this track all the way around the orbit until it gets to about here. Then it will be attracted by the Terra so that it increases its speed here. Then half a year later, it will be further away. It's kind of like the same mechanic here. This closest point is called a pericenter, or periapsis, or whatever. I'm going to call it a pericenter. And the farthest point is called an apocenter. A pericenter means that you're moving fastest. An apocenter means you're moving slowest. If you move faster at your pericenter, like if you accelerate at your closest point, then your furthest point will become further and your speed there will be slower. If you slow down, then your apocenter will decrease in distance from the star and it will become faster. This doesn't have to hold for just these 2 points. It can hold for any point on the orbit. Just draw a line to the exact other side of the orbit. I think, whatever. My point is, in this case, right here, the planet is coming towards the Glacial Terra. It's gaining on it, coming from behind. The Glacial Terra will pull it. It will add speed to it, so meaning on the other side, its orbit will be further from its current point, and it will be moving slower. And if it is moving slower as it is gaining, it will stop gaining and start receding. So, this object will never collide with the Glacial Terra unless its orbit is knocked so out of whack that it's not synchronized anymore. And then it may be able to collide with the planet. But that's an if, because if its orbit becomes too eccentric in this direction, it's going to be pulled away entirely by the gas giant and it's going to be ejected out of the system, or ejected out of the system. That's the only... Or it could be pulled into an asteroid belt orbit. If it goes inward, then it will be fucked with by both the Temperatura and the Glacial Terra. It'll collide with neither, and it will have its orbit be extremely unstable, to where it will either go inward the system, which I don't think is possible, or it will be thrown out again into the asteroid belt or ejected by the gas giant. But that won't ever happen. So this planemo is permanently between this point and this point, everywhere inside from the Glacial Terra, and it spends most of its time at around the exact opposite side of its orbit. It can get closer, but that's once in every 2,000 or 3,000 years. Every couple thousand years. I checked the simulation speed. It was every couple thousand years it got closer. So, I think... I don't know what I'm going to do. I don't know what I'm going to do when it gets to that point. But I think I'm going to have... whatever. I'll get to that point when I come to it. Anyway. This used to be a moon of the Glacial Terra, but it was pulled away by the star. It got pulled back into the same orbit, but it is now never going to see the Glacial Terra again from a close distance. Now for the other thing. So these two dwarf planets, I'm going to detail them later, but my simulations decided to spawn in a dwarf planet with an atmosphere. And, I was thinking, well, I don't think it's necessarily impossible for this object to not have an atmosphere. Although it would be very cold. So I don't really know. See, here's my plan. It will have an atmosphere. I don't know why it's brown. I think it's too close to the star to have methane and ethane in its atmosphere. Propane is far too sparse to congregate in an atmosphere at this point. So I don't actually know what this atmosphere is, but I'll look into it later. If there's nothing possible here, then I'm just going to change the color of the atmosphere. But this planet, or dwarf planet, it's called a planet, but it's really a dwarf planet. It will have an atmosphere. Is this called a planet too? No, that one's called a dwarf planet. Alright, well, you could consider this the fourth planet from the sun, but it's not really. So the Jovian planet is the fourth planet from the sun, or the star. Speaking of the Jovian planet, let's look at it. I'm going to edit its colors. I didn't mess with this at all. I messed with it a bit by giving it 3 moons. I tried to give them the same resonance as the Galilean moons. The fourth Galilean moon, Callisto, doesn't really have essential resonance. I don't think it has any resonance, and its orbit is really eccentric. Or no, elliptical. Not eccentric. Elliptical. Well, I think there's whatever. It has a very elliptical orbit, and it is just an ancient object. So whatever. I tried to give it a 1, 2, 4, 3 moon orbital resonance with 3 moons, but it slowed down the simulation, so I don't know what I'm going to do with the moons of this planet. I think I'm going to give them it 3 moons. I could give it 2 moons and have a third Callisto-type moon. I don't want to do exactly what Jupiter does, so I want to do something different. I'm thinking that the innermost moon will be an ice moon, and the outermost moon will be a Titan-type moon? I don't know what I'm going to do. Anyway, it's almost as massive as Jupiter. If the main star is this gives me something else to talk about. So, in our solar system, Jupiter was the first planet to form. It would have fallen closer inward if it weren't for Saturn, which pulled it back, which is why I have a Saturn-type object. This right here, the Jovian remnant, will act as both Saturn and kind of like Uranus in our solar system. It is also probably the most anomalous object. It's the strangest, but I'll get to it. The ice giant is like a Neptune, but this is kind of like a Saturn. I'll get to it. It being like Saturn because it pulled... okay, so in our solar system, Jupiter was the first planet to form. I already said that. It, for reasons that I don't understand and remember... God damn it, I let the playlist play for too long again. Other people might understand, I don't remember or know. Jupiter started to migrate inward. It was descending into the solar system, and it could have scattered the material that formed Earth so we might not exist if it spiraled all the way in and became a hot Jupiter. But Saturn stepped in and used its gravity to pull Jupiter from falling into the center of the system. So, because of Saturn, Jupiter is not a hot Jupiter. It's a Jupiter. So, if I wanted to have a Jupiter-style dominant gas giant, which I do, then I would have had another object or some other force stop it from falling into the inner solar system. I think it's a combination of it is less massive than Jupiter by a smidge, and there is a Saturn-type object in the system that pulled it back. Anyway, on to this one. It is or was a gas giant, this right here. But it is not a gas giant. You may be asking, why the fuck? is it a Saturn-type object if it's a terrestrial planet? Well, see, here. Let me remember. Okay, so it is a heavily watered planet. Has a lot of water. In fact, it is a frozen planet. It is a exposed gas giant's core. Yeah, gas giants have solid cores beneath their gas. My idea here is that there was some sort of catastrophic event midway through the solar system's lifespan, a bit after the late heavy bombardment, that caused this planet to lose its gaseous layer and become an exposed core. It could have been with the failure of its magnetic field entirely, which caused its atmosphere to be stripped away early on up to present day. It could have been a collision with an object that only scratched the outer atmosphere and kind of caused it to blow out through the solar wind, as it didn't have its magnetic field, so it just got ejected by the solar wind. It could have been any number of methods, but either way, this object lost its gas, its atmosphere, and it is now a airless Jovian remnant of a gas giant. Oh, that's fun. It doesn't really have any major moons. It's kind of like Neptune, but Neptune probably has a lack of moons because it migrated so extremely. This has no moons because it was changed entirely. It may have one Triton-type moon that's like a really weird moon that has a really eccentric orbit. It's not going to be retrograde, it's going to be prograde, but it lost a lot of mass. So if it held on to any of their moons, they will be extremely elliptical. And I don't know if that's possible, but I will try it. I did add a moon, and it was stable, so I can add a moon. Anyway, the ice giant I will also recolor, because disgusting. It's basically just like Neptune. In fact, I could add a side-by-side comparison of this ice giant and Neptune. Here, let me do that. Yeah, so this is a bit larger than Neptune. Who would have thunk it? And yeah, that's basically the solar system. My voice is really cramping from talking so much. So that's the system for you. Thank you for watching. I will get to more stuff. I'm streaming more with Stellaris. And I am uploading 2 videos, I think before this, that have to do with the... you'll probably have watched those videos, or you'll have the option to watch them. Wink, wink, you should watch those. I'm just amazing and a great content creator. But yeah, there's an asteroid belt here, there's a Kappa belt out there. I think the ice giant will have the extreme rings, like Saturn-type rings. Saturn got its rings because either a moon collided or surpassed the Roche limit and was torn to shreds. It's the guts of a moon, and they're short-lived. They're temporary. They're not permanent. So, this ice giant will have temporary rings. They're going to be hard to see from this far out. It's not that far from the star. If you compare it to our system, it's like 12 AUs. That's like the distance from on a Jupiter or Saturn. But this star is a K-type star, so it's dimmer. So it's the equivalent of Neptune's distance, or Uranus's distance, one of the two. It's an ice giant. So, if I decide that one has the rings, they'll be really hard to see. In fact, I don't know if this planet... It also has an eccentric orbit because it's the farthest object, just a little detail. It might be so dim that you can't see it from the temperate Terra. So it might be unknown through history. But I doubt that. I think that you can be able to see it. Let me go from realistic real quick. Look at all the planets. I'm sure you could see the Glacial Terra from the planet. But I don't think you can see the ice giant from this far. So I'm pretty sure that the ice giant will be a distance player. Anyway, yeah, that's the system. Also, you won't be able to see this, definitely. In fact, they won't know that anything's out here. They may detect that something's up because of orbits of comets, bright debris, because it's a really dark object. Even though it's mostly made of water, it has a really low albedo, so it absorbs a lot of light. It's a really dark planet, and it's far out, so they can't really see it. They may discover it on accident, like Uranus, but they might never discover it until they start looking. So, okay, well, they may know of its existence based on how it interacts with the orbit of something else. It pulls on other objects, maybe the Jovian giant, and the orbit of the giant, which they will know of, may be behaving strangely. And they may be like, why is it behaving like this? They may run simulations and calculations and predict the existence of an object about this massive at about this orbital distance, that if it is here, it can be the solution to changes in this orbit. But they will not have enough information about this orbit if they don't see it and verify its orbit and existence to predict the distance of this ice giant, because they won't know of any anomalies. They won't even know that it's there. They just might think that it's there and predict that it's there. But they might be able to see this at some point, like Uranus, late discovery, after all the legends and stuff, during like the progression of technology, like colonial age, something like that. They may see it and use its orbit to again verify the distance of a 1.5 Earth-sized object at this distance. A theory that is supported through here. So for a long time, they will think that their solar system only has 4 planets. They will know of the Planemo. They will not know of the remnant. They will know of at least one of these dwarf planets. Actually, no. It'll be another later discovery, these dwarf planets. So, yeah. The only objects they'll know of, since they have no moon, will be some asteroids, maybe. The Jovian system and its moons. The 2 other terrestrial planets. And the planetetesimal that orbits the same orbit as the Glacial Terra. Yeah. Alright. That is the end of the system. That is what they will know. And yes, maybe an update later. My voice really hurts, so I'm done now. This is almost an hour long. Goodbye.